So welcome again to another video. In this example, we are still on electric fields, right? This is another example that we'll focus on. So we're given a point charge that is creating an electric field, right? Already that's a clue to you. So we have this point charge, it's 8 microcoulombs and it's creating an electric field. So we are told to calculate the electric field strength at a point that is 0.25 meters away. Right, so most of the time, or actually in most cases, the formulas for finding electric field is F over Q or E is KQ over R squared. So depending on the information that you have, you would often know which formula to use, right? In this case, we do not have the force, but we have the charge, right? There's no way we can calculate the force nonetheless, so we can't use formula 1 to find the electric field strength. So as a result, what we'll do is we'll use formula 2 instead, which is E is equals to KQ over R squared. So that's the formula that we will use. Right, so as per usual, we like listing what we are given so that we know what we're working with. We're given the Q to be plus 8 microcoulombs. This is the same as 8. Actually, it's not approximately, it's literally the same thing as 8 times 10 minus 6 coulombs. And then what we also have is R being 0.25 meters, right? From there, we can then devise our solution. Right, so from this, we know that K is always constant, obviously. It's 9. It's 9 times 10 to the 9 multiplied by the charge that we're given. And we convert it to coulombs, not microcoulombs. Then we put the distance as well. Remember that electric field is a vector. So I get 1.15 times 10 to the power minus 6 newtons per coulomb. So in other textbooks, you might realize that they write it like this, newtons per coulomb. It's the same thing. Don't get it confused, or don't let it confuse you. Right, so in terms of direction, we know that an electric field for a positively charged object, never mind obviously it's incorrect the way I'm drawing it because the lines must be perfectly touching the sphere, and I'm just doing it fast, right? So it's usually something like this. So the way you determine direction is you imagine that if you place a point charge within the field that is being generated by this, if you place a positive test charge actually within the field that is being generated by this point charge, where will that test charge go, right? What force will it experience? So in this case, since it's positive and this field that is being generated is from a positive point charge as well, you will find that it will be repelled and go to the right, right? So therefore, we can decide that our direction will be to the right, or you can say away. Typically, since they didn't give us direction in the problem, we would say away from the charge. So that's how you decide the direction of your electric field. Right, so that is all for this video. Again, catch you on the next one.